Hello and welcome to writing decay equations. For today's video, you are going to need a couple of reference tables. You're going to need your periodic table as well as reference table N. In addition to that, a lot of people like to use reference table O. That's helpful too. So we're going to start by writing a starting isotope and indicating using isotopic notation the protons and mass. Decay modes are found on table N. We'll write that starting isotope on the left side of the arrow, and then the decay particle go on the right or product side of the arrow. We will then balance that decay equation for both our mass number as well as our atomic number. And then you'll be able to fill in that decay product, which will require the periodic table. So please watch out for paper cuts. So we're going to start with an alpha decay. So we're going to write a decay equation for the decay of francium-220. So I'm going to start by writing Fr. The 220 is the mass that goes on top. And then I'm going to find on the periodic table that francium is number 87. Then I go to reference table N to find my decay mode. So francium-220 has an alpha decay. You are going to want your mass and your protons for this. So the top number of the mass is 4 and the bottom number is 2. You may also write this as a helium nucleus, which is just an equivalent notation that's given on table O. So our starting isotope and then you draw your little arrow, you'll usually be given that anyway. Our decay mode is that alpha particle. And then we have to figure out our resulting isotope. So this is kind of like an algebraic equation where we have 220 equals 4 plus x for the top. So 220 minus 4 is 216. For our number on the bottom, we have 87 equals 2 plus x on the bottom. So 87 minus 2 is 85. Then I'm going to go to the periodic table. And element number 85 is astatine. And we always need to check ourselves so we don't wreck ourselves and make sure that everything balanced out and everything adds up properly. So we have on the top 220 equals 4 plus 216. On the bottom we have 87 equals 2 plus 85. Both of those check. Next you're going to write an equation for the decay of gold 198. So we start by writing a symbol for gold 198 on top. Gold's atomic number is 79. Then we're going to determine the decay mode. So we go back to reference table N. And it says B minus. Now remember, B minus and B plus are two different things. So you go to reference table O. This B minus or beta particle can be written, typically I write it like that, or you can write it like that, but you do need to make sure that you have a negative 1 on the bottom. So we're going to start with our starting isotope. And then we're going to fill in our decay particle, and then our resulting isotope. So we have on top 198 equals 0 plus x, so we're keeping 198 on top. A beta particle has such small mass that it is essentially like an electron. It is negligible. On the bottom, we're going to have 79 equals negative 1 plus x. So what we're really doing here is we have to add that 1 to both sides. So on the other one, it looked like we were always subtracting. We are subtracting here. We're just subtracting a negative. So 79 minus negative 1 is actually 79 plus 1. So we get an 80 on the bottom. So then I'm going to look up element number 80, which is mercury. So your nice piece of gold turned into mercury. Then we're going to check the tops and the bottoms. So on top we have 198 equals 0 plus 198. That checks out. On the bottom we have 79 equals negative 1 plus 80. That checks out as well. Next, we're going to do the decay for iron 53. Iron's atomic number, we're going to go to the periodic table and grab that, is 26. Our decay mode for iron 53 is a B plus, which is a positron. So you can write it either of those ways. Just make sure you've got a positive number on the bottom. So you're going to start with your starting isotope, 0 and a plus 1 on the bottom. So on top, it's 53 minus 0, remains 53. 26 minus 1 on the bottom, because remember this is 26, equals 1 plus x. It's going to become 25, and element number 25 is manganese. So on the top, we have 53 equals 0 plus 53, checks out. On the bottom, 26 equals 1 plus 25, checks out. We're good to go. Gamma rays, actually, you don't typically have to balance with these, but please just keep in mind that the gamma ray has 0 mass and 0 charge, so it can be there without really, it's a 0 and a 0 on it, doesn't really affect your balancing of these equations. And please pause the video for a minute, try these out, and then you can check your answers. After you've checked your answers to these, you can also use this kind of logic to determine the identity of a missing particle. So if we filled in our 5 for this boron, and for beryllium, we got to fill in a 4 down here, we can see on top that we would have a 0. And we have, this is 5 equals 4 plus x. So x is a positive 1, so that would tell us that this is a positron.